In natural language processing, the mathematical baseline for task adaptation is full fine-tuning. You maximize the conditional probabilities by repeatedly calculating a gradient update for every single parameter in the pre-trained architecture. For a massive architecture like the GPT-3 175 billion parameter base model, the raw parameter weights alone occupy approximately 350 gigabytes of memory. But the true hardware barrier to running backpropagation at this scale lies in the requirements of the Atom optimizer. For every individual parameter in that 175 billion parameter network, the hardware must maintain entirely distinct 32-bit buffers for both momentum and variance. This operational overhead effectively triples or quadruples the baseline memory footprint. Run the math on those states, and a single full fine-tuning run for a 175B model requires 1.2 terabytes of VRAM. Even if an organization secures that compute for training, deployment introduces a second physical limit. Hosting completely independent 350 gigabyte model instances for every downstream consumer application quickly consumes available server capacity. The mathematical reality of modern parameter counts renders full-rank updating economically unviable for production environments. To bypass the VRAM bottleneck, researchers looked to a concept formulated by Agajanian et al. Regarding the intrinsic dimension of overparametrized neural networks. This diagram represents a massive pre-trained weight matrix. The hypothesis states that while the base matrix is huge, the actual mathematical change required to adapt it to a new task occupies a highly restricted low-dimensional subspace. If the required change is confined to a small subspace, we can mathematically map the task-specific parameter increments into a newly defined, drastically smaller parameter set. This is the driving logic behind low-rank adaptation, or LoRA. The objective shifts from updating the massive base architecture to instead strictly optimizing this tiny new parameter set. Adapting a massive language model for specialized downstream tasks relies entirely on locating and optimizing this specific low-dimensional subspace. Prior to LoRA, the standard engineering response to the parameter bottleneck was to inject external modules, known as adapter layers, directly into the transformer structure. This schematic details the placement of adapters, inserted explicitly between the self-attention layers and feed-forward modules. The flaw is that placing a structure directly in the processing path forces a sequential bottleneck. Data must clear the adapter before moving up to layer norm. Large neural networks rely heavily on hardware parallelism to process data quickly. But by forcing sequential processing steps, adapters completely break that parallelism, a flaw that becomes highly visible in online inference scenarios where the batch size is just 1. The Microsoft research team measured this empirical penalty directly. Inserting adapters into GPT-2 Medium introduced an inference latency penalty of up to 30.3%. Other methods, like prefix tuning, attempt to bypass architectural changes by appending trainable special tokens to the input sequence. Reserving a portion of the sequence length for continuous prompts directly cannibalizes the usable contact tokens available for the actual task. All these methods enforce a strict trade-off. Engineers have to sacrifice VRAM, usable sequence length, or overall execution speed. LoRA avoids sequential latency by utilizing parallel injection. This schematic illustrates LoRa's core reparameterization. Instead of sequential layers, two low-rank matrices, A and B, are placed perfectly in parallel with the frozen weights. Because their rank is tiny, calculations run rapidly, and outputs are simply summed coordinate-wise with the base weights. To maintain training stability, matrix A receives a random Gaussian initialization, while matrix B is initialized to exactly 0. Because B starts at 0, the total update value at step 0 is identically 0. The architecture begins training behaving exactly like the unmodified pre-trained model. During backpropagation, the system only tracks optimizer states for these tiny matrices, yielding a 3x VRAM reduction and 10,000x fewer parameters. As we transition into deployment, the true mechanical advantage of this linear design emerges. Because the frozen base weights and the product of the trained LoRA matrices share the exact same output dimensions, we can explicitly add them together, they collapse permanently into a single merged weight matrix, replacing added layers with parallel projections that merge upon deployment. In doing so, LoRA achieves massive storage efficiency with mathematically zero added inference latency by design. The empirical data proves the efficiency. When evaluated on WikiSQL and multi-NLI datasets, a GPT-3 model equipped with a LoRA module containing just 4.7 million parameters matches or exceeds the performance of a fully fine-tuned 175 billion parameter model. This chart maps validation accuracy against the number of trainable parameters. Notice that prefix tuning exhibits a sharp performance drop when utilizing more than 256 special tokens. LoRA, operating in parallel, scales effectively as the parameter count increases. However, the most rigorous tests revealed an anomaly in the data. LoRA achieves parity using an internal rank as small as 1 or 2. A rank of 1 is highly constrained. It only reaches peak effectiveness when the low-rank updates are applied simultaneously to both the query and the value projection matrices inside the attention head, rather than allocating a larger rank to a single weight type. A 12,288 dimension matrix update is heavily overparameterized. A single mathematically targeted vector pair contains all the semantic data required to execute complex downstream tasks. How can an update matrix restricted to a rank of 1 capture the exact same behavioral information as a matrix with a rank of 64? To find out, the researchers performed singular value decomposition on 2 separate adaptation matrices, one trained with a rank of 8 and one with a rank of 64, extracting their right singular unitary matrices. This heat map maps subspace similarity using the Grassmann distance. The dark concentration in the top left corner indicates massive overlap between the top singular vectors of the rank 8 and rank 64 models. Outside that single dimension, the similarity drops to near 0. Expanding the rank does not cover a more meaningful mathematical subspace. Those higher dimensions are simply capturing random noise accumulated during the backpropagation process. When mapping the trained low-rank matrix against the original pre-trained weights, the researchers found a 21.5x amplification factor. The low-rank update isolates specific singular directions that already exist in the base model and drastically amplifies them. Fine-tuning a massive language model does not teach it new concepts. It applies a precise, low-rank mathematical amplification to the generalized features already mapped in the pre-trained weights. By exploiting this structural reality, LoRA isolates the exact data needed for adaptation, bypassing the hardware bottleneck entirely.